For the next lesson on our circle information, we're looking at the arc lengths and sector angles. So our goal is to be able to solve problems related to the length of an arc in a circle and the area of a sector of a circle. So for these things, we actually need our area and perimeter formulas for a circle, as well as the degrees in a full rotation. So we can start with the fact that the area of a circle is given by, so A for area is given by pi times the radius squared. The circumference, there's two different ways we can write this. Usually we know the radius of our circle and maybe not so much the diameter, so we often will write 2 times pi times the radius. Or we could write circumference is just equal to pi times the diameter, because it takes 2 radii to make up 1 diameter. So these formulas are will give you exactly the same thing. Now, as far as the degrees in a full rotation, we should know that there are 360 degrees in an entire rotation. So when we're looking at a sector of a circle, we're looking at just a fraction of that circle. So we're looking at how many degrees out of 360. So in this first example, if we want to find the area of this sector, our sector has a central angle of 54 degrees in here. That means I'm not going all the way around. The fraction of the circle is just 54 degrees out of the 360 degrees. That's the fraction of the area that we want. Now we could take that into lowest terms. If you have a fraction button on your calculator, that's really handy. But if I do that 54 divided by or over 360, put that in lowest terms, I get a 3 over 20. Okay, so 3 over 20, not 2 over 20. I want 3 over 20. So that's the fraction of the circle that this sector represents. So when I calculate the area for that sector, so the area of the sector, it's going to be pi r squared, but we only want a fraction of it. We want 3/20ths of the circle's entire area. So we take the area formula but times it by 3/20ths, because that's the fraction we need. So we're going to have 3/20ths times pi times 8 is the radius given for us. Now, sometimes you'll see things being left in exact form, and I'm just telling you this. I'm not expecting you to leave it in exact form, but if you go on to college and they want exact answers, you're going to leave the pi symbol there, and you're just going to calculate the number parts. So I'm squaring the 8, I get 64, and then I'm going to multiply that by 3. That gives me 192 out of 20 times pi, which could go lower in lower terms. 192 over 20 using my fraction button, and I get 48 over 5 pi. 48 over 5 pi. That's a 5 on the bottom. But as I said, we can take that actually to a decimal, so I'm going to times that by pi, and I get about 30 to one decimal place, 30.2. That's going to round up to. Okay, and that's area, so it's centimeters squared. It's square centimeters that we're covering that piece by. All right, similar thoughts in terms of finding your arc length. The arc length is the length of the outside part of that sector. It's that rounded part there. It's part of the circumference. So again, I'm going to put arc length here. Arc length is equal to just the fraction of the whole circumference. So it's 3/20ths of pi times the diameter, or 2 times pi times r. I'm going to actually do the 2 times 8 and get my 16, pi times my diameter. So I'll put that as a D for diameter. And the diameter would be 16 because it's 2 radii. All right, again, you could write this in its exact form. You can also simplify this right off the top rather than multiplying and then simplifying. I know that 16 and 20 are both divisible by 4, so if I divide 16 by 4, I get 4. If I divide 20 by 4, I get 5. So that's going to be 12/5ths as my fraction. So 12, I got that by taking the 3 times the 4 on the top, and then the 5 is just left on the bottom. Okay, but put that into your calculator. 12/5ths times pi, I get about 7.5 there to one decimal place. So 7.5 centimeters. And it's not squared because it's just a length. All right, so hopefully that's making sense. You're just taking a fraction of the area or the perimeter to get your sector area or your arc length. So the last example, this one's actually a little trickier. We want to find the shaded area of the diagram, which is a segment on that circle. So we want to find the area of that segment. Now, not so easy because I don't have a formula for that, but I do have a formula for the sector. So what I could do to start with is I could find the area of this entire sector, just like we did in the last example. So my central angle is 140 degrees, so I'm finding 140 out of the 360 degrees. So this is the fraction of that sector. So 140 out of 360 in lowest terms is 7/18. So we're really looking at 7/18 of the circle, a little less than half. I'm going to find the area of the sector, and then I'm noticing I have a triangle, and I know how to find the area of a triangle. I could take that area of the triangle away from the area of the sector, and that will leave me with that shaded blue area there. So why don't you give that a try? See what you can do with that. See if you can think through how you're going to find the area of the triangle, because the sector part's actually easy. And then from there you just subtract to get your segment area. So try that. All right, so the area of the sector, and if you've already got this, you can fast forward here. I'm not going to show you anything remarkable. 7/18 times pi times radius squared. The radius is 5, so 7/18 times pi times 5 squared, which will be a 25. I'm not going to bother with the exact on this, so we're just going to go to our decimal amounts. So 25 times 7 divided by 18 equals times the pi, so that would be 9.72, 30.54. I'm going to go to 2 decimal places on this, 30.54, and that's area, so that's centimeters squared, or square centimeters. Now I need my triangle, the area of a triangle. So the area of a triangle, hopefully you remember, is base times height divided by 2. Base times height divided by 2. So in that triangle, I'm going to use the chord as my base, but I don't have that length. Okay, so I'm going to let that chord length be x, or let the base of the triangle be x, or let x represent the base of the triangle. Okay, and if I look at that triangle, I know a side, believe it or not, I actually do know 2 sides, and I know the contained angle. I know the radius is 5 centimeters, so that means this other side is also 5 centimeters. They're equal, the radius is of the, that makes this, actually an isosceles triangle. I could actually solve for these angles in here. And eventually I want to get that side x, which is across from the 140. So we could potentially either use cosine law or a sine law on this question. If I want to solve for this angle in here, I know my angles in a triangle have to add up to 180. So I'm going to take off the central angle of 140. That gives me 40 degrees. And then if I cut those in half, so I'm going to take that answer, divide by 2. Take that answer, divide by 2. It gives me that those little angles there are 20 degrees. So I think we can use the sine law here. So x over the sine of 140 degrees. You could also use cosine law to solve for the x. That's going to equal 5, side length is 5, over the sine of 20 degrees. Okay, now from here, I'm just going to fix my writing. From here, I'm just going to multiply both sides by the sine of 140 degrees, and that's going to solve for what my x is equal to. So I've got 5 divided by the sine of 20, get that answer, and then I'm going to multiply that by the sine of 140 degrees, and I get about 9.396. That rounds up to 9.40. 9.40 approximately there. Okay, so that's the base length, but now I still need a height on that triangle. So the height, it is isosceles, so the height actually is going to meet the base at a 90-degree angle, and we'll cut that x in half, but I don't even need that because I can use SOHCAHTOA here. I'm trying to solve for the height, which is opposite the 20 degrees, and I know the hypotenuse. So opposite and hypotenuse means I could use the sine. So the sine of 20 degrees is equal to h over 5. We can solve that for h. So for 20 degrees, sine of that times 5, that gives me about 1.71 as my height. Whoosh, 1.71. Good thing I left lots of room for this question. So now I can get the area of the triangle. So the area of the triangle, my base is 9.40 times 1.71 divided by 2. So let's see what we get here. I got an 8.0, actually 8.04. Let's go 8.04 is approximately what I get from that. And I kept all my digits because I was, rather than typing in 1.71, I just took the answer from my last calculation. So now, final thing is we can find the area of the segment. The area of the segment is going to be the area of your sector, which was 30.54, minus the area of the triangle, which is 8.04, and that's going to give us a fancy-dancy 22.5 centimeters squared. And there we have it. A little bit of problem solving fit in with that, where we had to use some of our other tools.